The remote working security conundrum. What is reasonably secure anyway? Who am I? I am Alex. I was working with Andrew to build a secure development/sysadmin stack for OrionVM. So OrionVM is a wholesale cloud computing provider, which you can think of as infrastructure as a service. So a couple of disclosures. So we haven't received discounted products. Some of the things we're talking about are very much in progress. Specifically, some of the hardware is just shipping now, and so we can't independently verify the manufacturer's claims. One thing we can verify, though, is Qubes, because we've been using it for years. If you're interested in more information, look at our linux.conf.au talks about Qubes and its internals. So the key point from the talk title was reasonable. So what is reasonable? It depends very much on who you are and what you're trying to protect against. In our case, what changed radically was the commoditization of the exploit market. So what does that mean in simple terms? So commoditization is when something becomes a commodity. It's something that can be bought and sold on an open market. So the commoditization of the exploit market is when exploits went from being things that individuals made and then used into things that people were making for profit to sell to others, and things that people were essentially buying in bulk to execute considerably more technically complicated attacks than they would otherwise be able to. And so the effect of that is to reduce their cost per affected user, especially when attacking companies with larger customer bases, and it also increases the profit per attack. And you're seeing a lot of this in ransomware these days. It's also important to keep in mind that most of the value here is all in information. For example, the value of the laptop isn't the value of what it physically has, it's the value of what it can access, both in terms of personal information, along with potential business disruption and the like. So specifically, what isn't mentioned in this threat model are politically motivated attacks, because those are fundamentally, they're not economic, and social engineering attacks, because they require defenses that are not technical defenses. So the security pyramid, you can think of this very much like a building. Each layer is built on the lower layers. If your lower layers are not secure, then even if you can get a top layer to exist, it's only going to be a facade. The minute you put load on it, everything is going to fall apart. And so with that, let's start at the bottom, physical security. So physical security, you should have a screen that locks. Setting up an auto locker is again useful so that your machine will automatically lock when it gets removed from a dock or what have you. Setting a BIOS password and setting your machine to boot from internal disk only quite easily deals with a bunch of opportunistic attacks. A Kensington lock is just a straight up lock. If you lock your laptop to a desk, it becomes a whole lot harder to walk away with it. A screen privacy filter is a filter that goes on the top of your screen that reduces its viewing angle. So, for example, you can see what's on the screen, but if you're sitting in a plane or in a crowded room or what have you, other people can't be watching over your shoulder. Glitter screws are a very important sort of concept. So if you look at that picture on the right there, you'll notice that is a clear binder with a whole lot of multicolored particles in that. So when you apply that to a screw in 3D, those multicolored dots get deposited and then set in that clear resin. And that then provides a unique sort of pattern that is currently considered difficult to replicate. Now, you do need to check those from time to time, but it does provide reasonable assurance that nobody has gone and tampered with your machine. Anti-interdiction shipping is also an interesting concept. At the moment, it's somewhat niche, but it really shouldn't be. It uses techniques such as glitter screws to ensure that the machine that you ordered from the factory is the machine that you received. So, also on the physical layer, these are hardware kill switches. So they look somewhat superficially similar to a function key. So like you press a function key, and your OS mutes your audio. The difference is that a function key is a suggestion, a hardware key is a command. So your OS can quite happily say, well, I don't feel like muting your microphone right now, and there's nothing you can do about it. Whereas with these hardware kill switches, when you disconnect the microphone, it's electrically disconnected, and the software really has nothing to do with it. And so aside from the standard sort of attacks that you would expect, here are some unexpected attacks that having these hardware kill switches prevents. So the top reference is recovering passwords using nothing but audio. And keep in mind that even if you can recover 72% of keystrokes successfully, for those that weren't recovered successfully, as long as the real keystroke for the password is more likely than all other keystrokes, that exponentially increases the speed of a brute force attack. And down the bottom, that reference is for doing something similar just for physical keys with physical locks. So continuing on, we needed to go and do a fairly serious comparison between a whole set of different providers for this. And again, this is where reasonable is very much in the eye of the beholder, comes into its own, because depending on what exactly it is that you need, all three of these are all perfectly reasonable choices. So Intel and AMD, everyone knows, Power 9 is a chip made by IBM. It's open source, but it's expensive. So going past that cost row, RAM encryption and ECC. So AMD is unique here in that they have RAM encryption, which protects against cold boot attacks. So a cold boot attack is when you essentially just steal the RAM out of a machine and use the fact that it takes time for the capacitors that are storing the individual bits to discharge to try and extract things like encryption keys or other confidential data. So AMD deals with that by having RAM encryption. So there's an encryption engine on the CPU itself, and those keys are stored within the CPU and they get erased on power cycle. So the other guys do not have that. Power 9 has ECC though, which is also very interesting. So in general, you wouldn't take ECC as a security sort of property. Is generally used for data integrity, preventing from accidental bit flips due to cosmic rays or what have you. But it also protects against what are known as rowhammer style attacks, in which by exploiting the physical properties of RAM, you can go and change bits that you shouldn't be able to. So that is a win for AMD and Power 9 there. The management engine is very interesting as things go. So from an enterprise point of view, it's great because it allows you to easily manage a whole set of laptops or what have you. The downside is that it is a closed source sort of code base that has complete access to everything inside the system that the system cannot audit or manage at all. And in a lot of these cases, you have no source code and you have no way of knowing what's actually running on the machine. The big standout on this is the Power 9 that has an open management engine, which alleviates an awful lot of these concerns. And the other one is Intel. So Intel has the HAP bit thanks to the US government. So there's a US government requirement that their machines have disabled ME, which was reverse engineered. However, because of the way in which the management engine is actually implemented, it's loaded from the BIOS in segments. You can simply not load almost all of the management engine and still have the machine boot. And so what you're seeing is some BIOSes go through and do that, and so it's mostly removed for that. And so one major issue with the AMD is the AMD's PSP, which is their version of the management engine, can't be disabled. And then at the bottom, you've got Qubes and Head support. Qubes is an operating system, we'll talk more about in a minute. Heads is firmware. So by far the best support is under Intel. AMD technically has head support, but it's very old hardware. Power 9 is getting a Qubes port in that it's actively being worked on, but nothing is there at the moment. And because it's an open source sort of system, you could build your own given sufficient time. We also considered ARM and RISC-V, which were interesting, but but not really all that useful for this. If you'd like more information about that, please ask a question. So continuing on, so we chose the LibRem14, which is made by a company called Purism. So they're interesting in they're a social purpose corporation, which is half an open source security charity and half a company that sells things built on those open source security products. So you've seen some of their hardware previously because that was the laptop with the hardware kill switches. So they're using Coreboot as a BIOS, which is a Linux-based BIOS implementation. They use that reduced Intel management engine code that I was talking about previously. They also use Coreboot SMM code. So SMM is system management mode, so that is originally designed for laptops, but has the same issue as the management engine in that it has full access to all of your machine, but you can't audit it by default, and so it becomes a very common spot for rootkits and the like. And so their implementation of all of this is called PureBoot. So that is built on top of heads. And so what it can do is it creates a series of measurements as you're booting. So it will verify the BIOS itself. It'll verify your bootloader. It'll verify that the kernel that is booting is the kernel that was signed according to keys that you burnt into your version of the BIOS. And once all of those things have happened, it will use that to unlock the TPM, which can then verify to the LibRem key, which is a hardware security token you plug in, that your boot was successful, and then the key will flash green for you so that you know that everything's okay. And that is, again, very interesting because that's a good UI for what is fundamentally a very technically complicated process. They have an open source embedded controller, which does things like fans and battery charging. Not a big security thing, but still good. And they've also disabled, and we've disabled hyperthreading, and that's just to protect against microarchitectural attacks. So moving on, hardware security tokens. So the LibRem key that I was talking about in the last slide is to the left, and more standard YubiKey is to the right. They run in two modes. So you've got challenge response or HMAC mode. So for this, there is a key inside the crypto chip. So you send it a challenge, it hashes your challenge with that key and returns a response. And so we use that to secure LUNX keys as both for online attack and for offline brute force attack, because that crypto chip is tamper resistant. And it also slows down the number of requests per second that can be made. These security tokens also have a smart card mode, which can be used for things like GPG keys or SSH keys. So moving on for a second, TPMs. So they're very similar to a security token, except they're physically inside the computer, and they are unlocked via the boot measurements, as I mentioned previously. So if you look at the chip at the top there, that chip is tamper resistant. So it is considered difficult to extract the keys from that chip without having it cooperate by, for example, giving it the correct boot commands. The issue is that connector down the bottom is not tamper resistant. And so if someone can go and unscrew the laptop, they can man in the middle of that. And so that is part of why those glitter screws are so useful, to ensure that nobody can open that and make those modifications. And speaking of modifications, physical firmware protection is critical. So this is one of the boards there, and if you look at that black arrow with the red circle, those are dip switches protecting the write protect switch of the BIOS itself. And so BIOS rootkits have been seen in the wild. You've got Mebromi, which was lesser known, but the big one was Lojax, which was built by the Strontium group, which is associated with the Russian GRU. And there are many more, because again, much like the Intel ME or the SMM mode, like, it is a very interesting spot to go and put a rootkit, because it has full access to your hardware, but nothing really can verify that it is correct. So moving up a level, the operating system. So this is Qubes. It is a reasonably secure operating system. That's their tagline, based on security through isolation, which is in many respects the only security you can really trust. So the idea is that you look at what's known as the DOM0, which runs your GUI and all the rest. It also runs all of your applications in what are known as cubes, which are Xen VMs that can run their own OS, and they're all tied together via vChan, which is like Unix sockets between VMs running through shared memory. Qubes also deals with USB devices and PCIe devices using the IOMMU, which is a firewall for PCIe. So, to show you what that actually looks like in practice, here is an actual desktop. So what you're looking at is DOM0. It is a management VM. So it takes your key presses, it provides you with the screen, but it has no internet connectivity, and so it is very hard for things to attack it. Each one of those cubes is sandboxed within itself, and so it can't see anything else, which is demonstrated better in this picture. So in this one, you've got the disposable cube to the left, which is running a web browser, and so it can't see much aside from itself. And then on the right, you've got a password manager that again can see itself, but nothing else. And this is important as, for example, that web browser can't reach out and try to attack that password manager, as again, they're just sandboxed. So speaking of USB is a Lovecraftian nightmare because that USB key on the right there can be a keyboard, a mouse. It's a virtual Ethernet device with its own radio that can bypass your firewall. And it can be a storage device that can go and contain attack code, which, because it is emulating devices that are considered trusted, like, for example, a storage device, the drivers are not going to be as security-minded as things that are dealing with untrusted data. So, for example, file system drivers and the like. These also come in a USB cable form factor known as the USB Ninja, which is even more of a problem because, again, how often do people know exactly how many USB charging cables they've got and can identify all of them? So here's an example of a Cube's video call. So this is using a disposable cube, as we mentioned previously, but you've got some USB devices, in this case a webcam and a microphone that have been passed through. And so you can do that from DOM0, but from within that disposable cube, it can't see any of those devices, and from that sys USB, it can't see any of the web browsing information. And so that goes and protects everything. So moving on, hardware isolation is essentially the core of cubes. So if you look on the left there, you've got a disposable cube. It has no devices. That protects you both from hardware itself that is insecurely designed, that would allow for a confused deputy attack to allow that hardware to attack other cubes or the hypervisor or what have you. But it also gets rid of drivers. So as we'll see in the next slide, drivers are a massive weak point for security. Then on the right there, you can see cisnet. So that is the cube that takes your Wi-Fi card in particular, and it is considered insecure, and it locks all of that down. And so the key point there is that between all of the different attacks against Wi-Fi itself, the attacks against Wi-Fi firmware, because keep in mind that your Wi-Fi card is itself a machine running its own operating system that is both remotely accessible via its radio, because, you know, it's a Wi-Fi card, it has a radio, and generally has full access to all of your data because it's also a PCIe device. And so that makes it a very weak spot for security. And then as you move up on the stack, you've got all of the different pieces of software like DHCP clients and the like that have, again, found a whole series of attacks. And so what Qubes does, it bundles all of that together. It uses the IOMMU to lock it all into this cisnet cube. And then it says, well, hey, we cannot possibly verify that this is trustworthy, so let's just assume that it's untrustworthy and build everything else around that. So As I was mentioning a minute ago, drivers are incredibly insecure. So if you look to the left there, that is a Dell BIOS update driver, which is a problem because as we mentioned previously, there are a whole bunch of BIOS rootkits out there, and B, this is also why you want that that hardware write protect switch, because it protects you from all of these things. And if you look at that CV on the right, that was NVIDIA under Linux. So this isn't a Windows drivers a terrible thing. It's just a drivers in general a terrible thing. So continuing on, disposable cubes. So the point of a disposable cube is that it is a cube that you boot up for a particular purpose, so web browsing, so for example the video conference that we mentioned before, or in this case you're opening a document. And the idea is that as soon as you close it, it gets deleted. And so because that state is reset every time, it can't accumulate things like malware. And because it only sees, for example, the document that you're viewing, it can't exfiltrate data that it can't see. And this also comes with Thunderbird integration, so you can sandbox email attachments, because again, email attachments are a very common malware exploit vector. So speaking of Lovecraftian nightmares, networking security. So local routers are very rarely secured properly, partly because router vendors don't generally provide security updates, partly because they generally have insecure defaults. And then you have ISPs that do DNS man in the middle, and HTTP content injection for various reasons. So Qubes' model is security via network isolation. So that protects it directly from some CVs, so for example that CV on the right there, but more generally it makes it a whole lot harder to attack, just generally. So here is a fairly complicated slide on this. So on the right you can see that cisnet cube that I was talking about before, so that encapsulates the Wi-Fi and all of the surrounding sort of junk, and so that is considered essentially the untrusted internet. You've got sysfirewall that goes and makes sure that only connections that you're expecting can connect out to sysnet. Then working back again, you've got a series of VPNs. So if you're going for one particular example, look at that DISP1337. So that would be something like that video call example from earlier. So it would have access to the internet via that web VPN, but it wouldn't have access to local devices. And that's very important, as things like printers, especially printer scanners, have access to a whole lot of very interesting documents that various people would like to steal. They generally don't get security updates, and they are generally internet accessible, or at the very least local network accessible. So at the top and in the middle, you've got a work and a hobby cube. They've got access to their respective networks, but it's important that they can't talk to each other. So they're all isolated down. Vault can't talk to anyone, which is good for a password manager. And that DISP1234 also can't talk to anyone. You can think of it as, for example, the disposable cube we were talking about in that document example. So if that document was malicious, it can't exfiltrate data, partly because it has no data to exfiltrate, and also because it has no network connection to exfiltrate it through. So, continuing on. One interesting point of this is the update path. So DOM0 has no internet connection, and so the obvious question is, how do you update it? And the answer is via sysupdate. So the idea is that sysupdate runs a modified and a smaller version of a standard Fedora update system. However, rather than actually installing the packages itself, it simply creates all of the files, and then DOM0 copies those back over via vchan, verifies those GPG signatures, and then does the local installation. And so this is very important because now you don't need to trust almost all of your update mechanism. Just as long as those packages that you get are GPG signed, and you can trust that nobody else can create GPG signed packages, then you can go and trust those and install those. And that's very important because if anything manages to get compromised things into DOM0, then essentially there is no more security in the system. This path is also looking to be used for secure firmware updates. via FWUPD, and that was made by 3MDeb. So as sort of an example here, you've got a BeyondCorp model. So to kind of define things here, BeyondCorp is designed for larger enterprises where it is simply infeasible to assume that you can maintain a trusted network, and so you don't. Instead, you say that your network is untrusted and all accesses to everything must be authenticated at the application layer. Now, there's a bit of ambiguity here. So Qubes has a thing called vaults, and HashiCorp has a product called Vault. They are not the same thing. They both just are called Vault because they both have to deal with passwords and the like. So in this example, there is some plumbing that is overlooked here at the top there in terms of just that box labeled Qubes. But the idea is that you have some local scripts that can access, for example, your local Qubes vault, like a trusted key there, can access maybe the TPM state information. But either way, it can prove that you are you. Because as sort of an example, those TPMs have certificates built into them that verifies that who they are in particular. And so you can use that to verify that, for example, the laptop that is sitting in a person's desk is the laptop that they are meant to be using. So you take all of that information, authenticate to HashiCorp's vault, which is being run on your corporate network. They then give you access to various things. So one example here would be a database. So you've got access to this database. So through some plumbing, you ask HashiCorp Vault to create you some ephemeral credentials for that database. It then logs into the database, creates those credentials for you, passes those back into Qubes, which can then pass them into a disposable VM, from which you can then access the database, do what you need, and then as you close that disposable cube, those ephemeral credentials can be expired. One other alternative here is, if you look at DISP1337 again, you can use split SSH or a U2F proxy. So split SSH, split SSH uses SSH keys that are stored on either a security token or on your cube, your vault cube, so that the SSH private keys are never accessible to the disposable VM. And the second thing is a U2F proxy. So that's actually implemented by Qubes and is upstreamed. And so that allows certain keys from your security token to be used to authenticate your browser to that business system. So continuing on, backups and business continuity. Qubes comes with local backups. Those are generally very good, but they are somewhat inconvenient. And the issue with inconvenient backups is that they don't get run, and backups that don't get run can't help you. We're looking to build remote backups, built around that separation of powers principle. And the key point of that is to make sure that the credentials needed to create more backups cannot also be used to delete existing backups, because that's how you end up in a situation where, for example, ransomware goes and attacks your machine, deletes all of your previous backups, and then you are very, very much stuck. And so we call this the TASNet model because they were the first to use that we've used. But there are quite a few other alternatives there. So going forward, we're looking to upstream the work that we're currently working on. Remote attestation is what I was talking about previously with the TPMs. So the idea is that the TPM, rather than simply verifying to the Librem key that you are that your boot process was good and that everything was okay, you can use that to attest to, for example, your HashiCorp Vault server, or to whoever else that the version that your machine is essentially running a good configuration. We're also interested in the Librem 5 for a possible mobile phone solution, and we're looking for better solutions for file or secret sharing that built on these Qubes primitives. Thank you very much. Are there any questions?